In this video, we are going to learn group actions. For the motivation, let's consider a group G. Is the rotation group of a square whose vertices are labeled 1, 2, 3, 4. And then we have 4 elements in G, say E, rho squared, rho cubed, where E is the identity rotation, which does nothing, and rho is 90-degree rotation counterclockwise, and then rho squared will be 180-degree to 70-degree rotation counterclockwise. So if we apply rho to the square, then the label will change it like this. So in this case, we are going to write rho as a permutation of the vertices 1, 2, 3, 4. 1 is in the position of 2, so we write like this: 2, 3, 4, and 1. So we can think of this as 1 moves from this position here to this position, and 2 moves from this position to this position, like this. So this will be the permutations, which stands 1 to 2, 2 to 3, 3 to 4, 4 to 1. So each rotation permutes the vertices. If you focus on the vertices, then we can see that this rotation permutes the vertices, but we can also focus on other things. So we can also observe that the rotation or any motion of this square also permutes the diagonals. Okay, so let's consider the diagonal. So the labels are like this, and now we have 2 diagonals. So here, the diagonal D1 is the diagonal connecting 2 and 4, so let me write this as a set like this. And another diagonal is, say, D2, which is 1, 3. So there are 2 diagonals here, and if we apply rho here, we will have a similar situation. And now the red diagonal will be here, the blue diagonal is located like this. So rho moves, so D1 to D2 and D2 to D1, because here D1, this is D1. If you do the rotation, this will be located in here, which is D2. So we will understand this movement like this. So it means that rho can be understood. Rho can be understood as a permutation of D1 and D2. So we will write this rho bar, which is a permutation of D1 and D2 in 2-line notation. D1, it sends D1 to D2, D2 to D1, so it's like that. Okay. Now, what about the rho squared? Rho squared, if you consider this as a permutation of the diagonals, you will move nothing. So D1 goes to D2, D2 goes to D2, something like this. So we have this. Okay. And we want to consider this kind of situation in general. So we want to define the following. This is a definition. So G is a group, and X is a set. So we say that G acts on X if for every element, say G, for every element G, there is a permutation G bar on X, permutation of the elements of X, and satisfying the following condition. So for any two element G, H in G, we can consider G their operation product G product H in the element G, and we can, because it's a group, also group element, we consider the corresponding permutation, and this will be the same as the composition of the two permutations obtained from each group element. We want to have this condition. This is a definition. Okay. So this definition may look very abstract and hard to understand, but it really represents the previous example. So I want you to think of G as motions, like rotations or reflections, something like that, that move elements in X. So group element is a motion, and the elements in X are the object that we move using this motion. Like, so elements can be vertices or edges or diagonals, things like that. And group action is really an abstract definition of this movement. Alright, so let's see some examples. So R is the group of rigid motion. Of a cube, so it's going to be a root. It changes. It rotates the cube. So then, and X is the vertices of a cube, and then the group R acts on X as follows. There are many rotations in R, but let's consider. So it's 1, 3, 4, 5, 6, 7, 8. This is the vertices, and let's consider this rotation where we rotate about this axis 90 degree. Let's say that's let's call that rotation sigma. Then what we get after this rotation for the group action, we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it permutes the elements in X, which are vertices. So we will write this as a permutation of the vertices 1, 2, 3, 4, 5, 6, 7, 8, and 1 is in the position of 2 now. So 1 is, it sends 1 to 2. and 2 gets sent to 3 and 4 and 1, and 5 is now in the position of 6, so it's going to be 6, 7, 8, and 5. So this is the permutation of the elements in X. And you can check that this definition respects the group operation, meaning this, you can check this. For every two group elements in R. So it is group action, right? And we can also consider the same group R and then different object. So instead of vertices, let's say Y is the faces of cube, and R also acts on the faces. So let me label the faces using alphabets A, B, C, and then here say D, the bottom, E at the back, F, let's say. And if you do the same operation sigma, then what we get is that A stays there, A is still the same, E is still the same, and B is now in the previous position of C. So it's B and C is in the back, F is on the left, and D is in the front. So in this case, sigma, shall we write sigma tilde, just to distinguish sigma bar over there. It permutes the faces A, B, C, D, E, and F. A stays there, E stays there, and B is in the position of C, so B goes to C, C goes to F, F goes to D, D goes back to B. So it is a permutation of the faces. The group action is like this. Okay. All right. Now let's consider group action on colorings of a set. Okay, because we want to consider colorings over vertices or faces or edges. So let's say X, we first need to define a coloring, and a coloring of a set X with colors, say a C1, suppose there are K colors available, then a coloring is nothing but a function F, say F from X to the set of colors. So example, X is the vertices of a square. So it's really just 1, 2, 3, 4 if we call the vertices 1, 2, 3, 4. And the colorings of, so all colorings of X with color say black and white are the following. Actually, I think there are too many. Something like this. Let me call it that way. Something like this. Let me just consider two of them. So it really is, let me use a different color, but maybe we can, let me just consider two different colorings. You just assign a color to each vertex. Maybe it's W, W, something like that, or W, B, B, B. These are examples of coloring. So F is this, and let's say G is this. And I represented this coloring using just a diagram, but if you want, you can write this as a you can represent like function f of 1 equals b, f of 2 equals b, f of 3 equals w, f of 4 equals w, or we can also write f as set of pairs. So 1 comma b, which means 1 is colored with b, 2 comma b, 3 comma w, 4 comma w, something like that. You can also do write g in this way. All right. So really, if f is a coloring of x, then we represent we also write f as a set of tuples pairs like x comma f of x, where x is in x, like I did just in the previous line. So definition, let's say G is a group X on X, then we can also then we can well, let me say this like, then G also acts on the colorings in the standard way, colorings of X by the following. So now the set of coloring is now Y. Y is the set of colorings, and G acts on Y as follows. So if it acts on Y, every element should be a permutation of Y, elements in Y. So let's say G double bar, and coloring is X comma f of X. Okay, element equals G bar X f of X. Okay, and then so here G bar is permutation of X because it sigma acts on G acts on X. We have this permutation, corresponding permutation, and we define a new permutation sigma double bar, which is now acting on the colorings, and the action is defined like this. Okay, so and the sigma bar is a permutation of Y, it's coloring. All right. Okay. So let's just consider an example. So D4 acts on the vertices. X is the vertices of a square. So 1, 2, 3, 4 basically. Okay. and Y is colorings of X with black and white. X using with black and white. Black and white. Okay. Then D4 acts on Y by following diagram. So 1, 2, 3, 4. Consider one coloring W, W, J, W, and B. And if you do this 90-degree counterclockwise or clockwise rotation, then we have B, W, W, W. Okay. So what is the coloring correspond here? So here the coloring is 1, B, 2, W, 3, W, 4, W, and it moves sigma double bar. It will move these two. It change sigma bar. Sigma bar. What is sigma bar? It's 1, 2, 3. It's permutation of 1, 2, 3, 4. 1 goes to 2, 2 goes to 3, and then 4 and 1. So sigma of 1 is 2, so it's 2, B, and 2 goes to 3, so 3, W, and 4, W, and 1, W. Okay. So here, so 1, 2, 3, 4 is changing to maybe just coloring. We are focusing on the coloring. So now here B has color B, so it's P here. W. 2 has color B, so it's like this. So it really rotates the figure, and that's the definition of the action on the coloring. Okay. So sigma double bar moves coloring to another coloring. It changes the coloring to another coloring. Okay. All right. Now we need to define orbits. For example, again, let's say D4 acts on say set X, which is the set of colorings of a square, vertices of the square with exactly 2 blacks and 2 white. So if we can list them all, like B, B, W, W, B, B, W, W, B, B, W, W, B, B, W, W. So there are 6 elements like this. Alright? There are 6 elements in this set S, and D4 naturally acts on this set. Now let's see what happens if you apply some elements, group elements, to the colorings. So if you do this rotation, you can see B, B, W, W. And if you do the rotation row, it's a 90-degree rotation. If you apply a rotation again, you get B, B, W, W. If you apply the rotation, B, B, W, W. And if you apply the rotation to this, B, W, B, W. So these 4 elements can be connected by the group element by applying if you apply the group action, you can go from one element to another, one coloring to another. So here, any two elements in this block, any two elements or colorings can be obtained. Okay, they can be connected by a group action. Also in here, any two elements, if you take any two of them in one block, you can go from one to the other by applying a series of group actions. So these kind of blocks are called the orbits. So G acts on X, and then for an element A X in a X, the orbit containing X is denoted G of X. G X, and it's a set of all sigma applied to X for all sigma in G. This is the definition of the orbit. Okay. So in the previous example, there are two orbits. One orbit has 4 elements and the other element has 2 elements in it. And you can see it covers all the 2 elements here. These are 2 orbits, one orbit over here, another orbit over here, and they cover the whole set S, and they don't intersect at all. So it's a partition of the set. So the theorem, basic theorem, is that the orbits of action G on X form a set partition of X. Okay. And our main goal, our main question is this: how to compute the number of orbits. So we have a group action acting on a particular set, and we want to compute the number of orbits because these are what we are interested in. In the previous example, the number of orbits in the previous example over here is equal to the number of distinct necklaces with 2 black beads and 2 white beads. We know that there are only 2 because black, black, white, white, black, black, white, white. There are only 2 necklaces using 2 black beads, 2 white beads, because everything else can be obtained from one of these by applying this rotation or flip. So we want to compute the number of orbits when you have a group action. And we will do this in the next video.